Tim, we have a bit of an audience, so it's a bit smaller than usual, but yeah, that's the time of the year.
No problem.
So let me use this opportunity to introduce you. Well, we all know, and I think the people here are all regulars, but yeah, the CSAT seminar, so in this time of year, it's mainly students presenting their work, and today we have Tim Heiszwolf. Tim did his bachelor end project with me. You all know that we are working on machine learning for modeling atomistic interactions, so basically deriving a potential energy surface for, well, deriving a methodology to create potential energy surfaces for different atoms and for mixtures of atoms. Some of you might have attended the presentation 3 months ago, I think it was, a presentation from a master's student, Robert Mollevaaler. That was the initial project, and we are continuing along this line of work. And basically, we have arrived at the conclusion that we really need a good testing framework to test the method, the machine learning method itself. And what Tim will present today is a method to create basically a toy model. It's not a particular atom interaction, it's not DFT based, but a model that can be used to create databases for interactions that can be used to test the machine learning methodology. So with that, Tim, I give the floor to you. And yeah, in terms of timing, we expect you to talk about 30 minutes or so, and then thereafter we have 10-15 minutes of questions. Yeah? Go ahead.
Perfect. Well, welcome everybody. I'm Tim Heiszwolf, and while sadly I wasn't able to see any of you in Differ due to Corona, I would still like to tell you what I've been doing these past few months of Mystical Month. Well, first I'm going to explain to you what the problem is that I tried to solve and which goals and requirements I had. Next I'm going to tell you a bit about some background information regarding potential energy surfaces. Then I'll tell you a bit about the solution that I made, including the toy model itself, some of the extra features the program that makes the databases has, and how the databases can be prepared for machine learning. After this, the results of the toy model will be discussed. This includes things like the speed of the algorithm, the quality of the databases, and a bit about machine learning. And finally, I would like to tell you a bit about the future and continuation of this project. Now, this entire project is about potential energy surfaces. As you all might have known, a potential energy surface describes what the potential energy is as different degrees of freedom change. The classic example, of course, is the ball on a hilly surface. Here the positions are the degrees of freedom, and the height directly corresponds to the amount of potential energy. Well, this is such a nice way of representing it. These are often used to visualize such a surface. But alright, what are they used for? Well, in the fields of physics and chemistry, potential energy surfaces are used to calculate the properties and applications of certain materials. Well, potential energy surface is crucial when developing new batteries, solar panels, but also when developing a TV. When investigating the properties of these materials, but also when designing the new materials, it's also crucial. Now, these properties are often difficult and expensive to test, and thus are more often investigated using computational methods. But sadly, these calculations of these potential energy surfaces or the associated forces takes quite a long time. Well, with machine learning, a bit of accuracy can be sacrificed to make these calculations significantly faster. Well, in this presentation, I will present a framework for the rapid generation of training data using a toy model, which can then be used for machine learning for hyperparameter optimization, after which such a design of such a neural network can be used on real reality-based data. So the goal is to make a fast testing framework for using machine learning on potential energy surfaces as an alternative to real simulations. Well, this consists of 3 parts. First, the toy model for potential energy. Next, the software that generates the databases. And finally, some neural networks should also be tested to see if the framework is usable. Well, the potential energy has several requirements. Well, first of all, the energy should depend only on position and take into account the infinitely repeating boundary conditions that we put around it. It should also be somewhat complex and non-trivial for a machine learning algorithm to learn. It should be symmetric, so both translationally and permutationally symmetric is needed. So for example, if we have a square, we should be able to move it, and the energy shouldn't change, but we should also be able to swap the particles, and the energy shouldn't change. Well, the energy should be continuous and continuously differentiable, because otherwise we cannot use it for the kind of calculations we want to use it for. It should also display physical behavior. So imagine if two particles come close together, they need to repel each other. But if they're at a larger distance, they also need to attract each other. The potential energy function should be quite general and abstract, such that it can be easily modified. And finally, calculating the energy with this toy model should be faster, easier, and more flexible than using a real DFT simulation. So, next we're going to generate a database, which of course also has some requirements. First and most importantly, it should contain a reasonable range of energy. So the energies have a nice spread, but extremely high energies should not be common or even not occur at all. The input should also behave well, since the database is going to be used to train a neural network. This means that the input should be symmetric, just like the potential energy, and the input should be continuously differentiable. Well, this is because we want the network to also be continuously differentiable, and thus the inputs also need to be so. Finally, a neural network should be trained and inspected. The requirements are that it should be somewhat accurate, and more importantly, that the derivative of it behaves well, since that's ultimately what we care about. Well, there are two major methods for calculating the potential energy surface from a certain configuration. The first is density functional theory simulations, or DFT. These simulations use quantum mechanics. The calculations are quite good, since they can be very accurate and can be very generally applied to many types of systems using many different types of atoms. But sadly, this method is quite slow, and sometimes many calculations are needed before it's accurate. Another methods are toy models, and that's what we're going to be using today. So it can be very useful to investigate how these work. These work by taking a sum of pair, triplet, quartet interactions, etc. Using only pair interactions is usually good enough for a lot of applications, but some applications require higher term interactions, such as triplet interactions. Two well-known pair interactions are those of Morse potential and those of the Lennard-Jones potential. These depend only on the distance between the atoms and thus are symmetric. They are also continuous and quite easy to compute. They consist of a short-range part, which dominates when the particles are close together and then asymptotically approaches zero, and a long-range part, which is negative, but dominates when the particles are quite far away. When added, they form the interatomic potential. The Morse potential consists of two exponential functions with a minimum at a certain characteristic distance, which has a certain characteristic energy as the depth. Now, due to the way it's constructed, the width can also be adjusted, and the minimum is approximately a harmonic potential, and this is very nice. The Lennard-Jones potential has a similar construction, but uses a 1 over r construction. Alright. So next we're going to design the potential energy function that we're going to be using. For the lattice, we choose a structure composed of square unit cells, or cubic unit cells, with a certain width. Each unit cell contains a certain amount of particles NP. The lattice has infinitely repeating boundary conditions, but since we want the computation to finish, we're only going to take into account a certain depth of some surrounding cells called ds. For example, here you can see a lattice with a depth of surrounding cells of 1. Of course, the depth of surrounding cells needs to be large enough such that the potential energy has converged, but a larger depth also means that more particles need to be taken into account, and thus more calculations have to be done. When calculating the potential energy, we will take into account only triangle interactions or triplet interactions, since pair interactions are quite simple. Higher could also be done, but that will greatly increase computational requirements. Also, we're going to calculate the potential energy per particle, since otherwise it won't converge very nicely. When calculating the potential energy per particle, one will take the sum of every possible triangle in the lattice, but this is computationally suboptimal, since the algorithm scales with the depth to the power 3 times the dimensions times the number of particles to the power 3. Well, for this method, the depth of the surrounding cells also needs to be quite large, since otherwise the edge effects will be significant. A better approach is to calculate the amount of energy per particle only in the central unit cell. Now, this can be done by only counting a triangle or triplet if at least one of the particles of the triangle or triplet is in the central unit cell. Now, this is the advantage that it scales much better, but also that the depth of surrounding cells that is needed for good convergence is significantly lower. This is because the edge effects only come from the central unit cell. Well, You might think that the amount of computations can be reduced even further by not counting each triangle multiple times, but sadly, only counting each triangle or triplet one time will not work very well. This is because it will result in an energy that's not symmetric. For example, here you have the potential energy of a square. We place a square in the center of such a unit cell and we slowly expand it until it reaches the edge. And you can see that's not symmetric. Well, why is this? Because it should be equal, since this configuration is equal to this configuration only translated to the edge. Well, this is because a triangle which would only be counted a single time in this configuration is counted 3 times in the other configuration, and thus you see also an energy that's approximately 3 times as small. Now, this method does work if you take into account every single triangle, like the method proposed initially, but as said before, this requires even more computational powers, and thus it is not used. So now we only need the potential energy function for a triangle, and the toy model is done. Well, we want this potential energy function to have a characteristic distance RC and a characteristic energy. This makes the equation more easily adjustable. For the characteristic energy, we chose a triangle with an equilateral triangle, and the characteristic energy is the energy at which it is minimum. The characteristic distance is the length of the side of such a triangle at which it is minimum. Well, next, several potentials were tried to find the best one. Well, the first toy potential that was tried had a short-range potential that depended on pair interactions, but was made complex by multiplying it by the area squared of a triangle. The long-range energy in this case was based on the circumference of such a triangle. But sadly, this function did not converge very well, as you can see. This is because if, for example, 2 particles are close together, but a third particle is very far away, then the pair potential, the pair term in the short-range potential will still be very large, and the area, of course, will be even larger, and thus it will continue to grow as you increase the depth of the number of surrounding cells. Well, next, we tried to learn from this and adjusted the short-range potential to also contain the circumference, but sadly this also didn't work. This doesn't work because if you then look at the repulsion, how the repulsion works, it doesn't work very well. So as a test, we placed 2 particles at half a characteristic distance from each other, so they should repel each other, and then the third particle moves away and towards from those 2. And as you can see here, this is the graph of the third particle. You can see that for long range the potential becomes nearly 0, and for short range it even becomes negative. So why is this? Well, the circumference always stays at least 1 characteristic distance, but the area, of course, becomes 0 if the third particle is on top of those 2. So this also can be used. Well, so it was decided to add back in pair interactions, since otherwise repulsion or conversion couldn't be properly achieved. We still wanted the single equation to be applicable to both pair and triplet interactions, so as an input, the average relative distance between each particle was chosen. So for a triangle, that is the circumference divided by 3, and for a pair, it's just the distance between them. Well, for the equation itself, the Lennard-Jones potential was modified in such a way that it converged after a certain distance called R0. Due to this, a correction term was needed, because otherwise the gradient wouldn't be continuous. The result can be seen here. The characteristic distance and energy are also not exactly in the position we want due to the modifications, but luckily, as long as R0 to the power n is much larger than Rc to the power n, the characteristic distance and energy are approximately in the right position. Well, we chose a n of 6 because we want to make it look a bit like the original Lennard-Jones potential. An R0 of 2 times the characteristic distance was also chosen to ensure a relatively fast convergence. And as can be seen, the results are actually quite good. You can see the potential energy surface itself here. It functions quite nicely. You can see the test of the square, the symmetric square again. You can see it's nice and symmetric. And you can see it converges very fast, in fact, after only a single depth of surrounding cells. So next, the software to generate the database was written. This was done in Python because of the ease of development, popularity, and my own experience in it. For generating a database, there are many settings which can be adjusted. For example, how many particles are in each cell, what the depth of the surrounding cells is, the number of dimensions that the database has, what the range of cell widths are. So for example, you can have small cell widths, large cell widths, and then how many parts that range is divided. It also contains some methods which can be used to adjust the distribution. For example, you can cut off the top few percentages of the energies, but there's also a method that can be used to lower the energies of the distribution. This is done by a sort of gradient descent-like relaxation method. The particles start, of course, in their randomly assigned locations, but during each scan of the relaxation process, they have the opportunity to move in a random direction with a semi-random limited magnitude. If this results in a total energy that is lower than the starting position, then the particle moves, otherwise it doesn't. Depending on how many scans are used, this allows the particle to come closer to the local minimum or away from the local maximum. And thus, the entire distribution has lower energies which are more representative of real energies. Alright, so now that we have a database, we can begin training a neural network, right? No, but nearly. We need to decide what inputs are going to be picked for the neural network. The obvious choice is just using positional data, but this is not a good solution. This is not symmetric. For example, imagine we have the square again, we move it, now the coordinates are all different. One of the other possibilities is just using the relative distance between each particles, since that is also what the potential energy function uses. We then only need to sort it to make sure it's symmetric, and then it will be all good. Sadly, also all know, this because while it is symmetric, it will result in inputs and thus also outputs which are not continuously differentiable. Imagine you have three particles on a line and the middle particle is slightly closer to the lower particle than the upper one. Now we start moving the middle particle upwards, and as it approaches the halfway point you can see a problem starting to occur. Because as soon as it's halfway, the relative distances of course will cross and thus will swap position, but the derivatives will stay the same. So we have a problem because now we have a discontinuity in the derivatives of an input, which we don't want. Alright. But what can be used then? Well, we know that ordinate eigenvalues of a matrix are continuous and will never cross if the values in the matrix are also continuous. This is called the no-crossing theorem. But what should the elements of such a matrix be? Well, this is the answer. It's called the proximity. And to calculate the proximity of order O for particle I and particle J, you first calculate the relative distance and then enter it into this function. It is sort of like a 1 over r to the power O function, but it has convergence built in at r0p. You then repeat this for each equivalent of I in each other cell in the lattice around it and take the sum of that. And the reason these equivalent particles are taken into account is so the neural network can also get a feel of how the neighboring particles of other cells around it interact with the particle in the central cell. You then calculate this for every combination of I and J and enter it into the matrix. And this results in a matrix that is the number of particles by the number of particles. Of course, this only produces an amount of inputs equivalent to the number of particles. So you need to make the same number of proximity matrices as star dimensions, because otherwise the system will be underdetermined. So, now that we can generate our database and then prepare it, how does it perform? Well, quite well in fact. It scales worse, or it scales equivalent or worse than DFT simulations. It of course depends on which algorithm is used. But the prefactor is much smaller since it's just a simple analytical solution. As you can see here, you can see the time required as the depth of surrounding cells increases or as the number of particles increase. And you can see that especially for a low depth of surrounding cells, which is needed, or low number of particles, it performs exceptionally well. The speed at which the preparations can be done is also important, since that is what ultimately decides how much faster the trained neural network is compared to DFT simulations. The construction of proximity matrices scales like this, and taking the eigenvalue scales like np to the power 3. Although this depends on which method is used to calculate the eigenvalues, but here we just use a general algorithm. This of course needs to be done for each dimension, so in reality another factor d is added. Again, a test using real computations was done, and it took around half a second per data point to prepare a database of around 20 particles, which is actually quite good. One of the questions with generating a database is, of course, how much the relaxation process should be applied. So to test this, I made a couple of databases, each with a cell width of 5 times the characteristic distance and 4 particles in it, and did different amounts of relaxations. Well, the resulting distributions can be seen here. And as you can see, for a high number of particle scans, the distribution seems to flatten at the bottom. They all seem to get the same value. Also, for some reason, the higher energies seem to become more common and more prevalent. I don't know why this is, but luckily this is not a problem since we can just cut those off. Why the lower energies become closer together is a problem. This is because if you then inspect the lattices, you can see a pattern starting to occur. Certain configurations seem to become way more prevalent. The particles seem to form either pairs or triangles or squares. And this is very bad because this means that we won't have a database that is very diverse. And we want, of course, a database that is very diverse so that the network can be trained properly. One of the ways to quantify how much this has happened is the acceptance rate of the last few scans. Well, the acceptance rate is the percentage of particle movements which are accepted. And while not completely scientific, I found that an acceptance rate of around 20% seemed to result in the optimal solution. Now, this corresponds to around 30 to 40 scans, and in such a database, configurations like this can be seen a lot more, and as you can see, it's quite nice since it hasn't formed a square yet and has quite a diverse set of energies. It's also important to note that the amount of scans needed varies with the size of the cell. In general, the amount of scans needed scales directly proportional to the size of the cell, but this has the disadvantage that it takes longer to calculate a larger cell. Another option is to scale the maximum step size allowed during each scan, but this has the disadvantage that it becomes a lot harder for the particle to find the local minima, since it's much more likely to overshoot such a place. Also, due to the building convergence of the potential energy function, for large cells, this method might not work very well at all, since the acceptance rate will always be very high because the change in potential is always zero, because the potential is always zero. Next, a database was generated which had a range of cell widths from 1.5 characteristic distances up to 10 characteristic distances, and this was also inspected. And as you can see, it looks quite good. You can see when the cells are very close back together, you can see the energy is quite high. And then as you expand it a bit, you see a minimum. This is when the particles are in optimal distance from each other in the cell itself, but also with respect to particles in the surrounding cells. And then as the cell becomes even larger, you can see that the energy starts to become way less extreme because the particles start only interacting with a few other particles in the main cell itself. Finally, to test how good the databases were, some machine learning was also done. This was first tried on a database containing a range of cell widths, but little results were achieved here. So then it was tried on a single cell width of 5 RC. And this did have success. The size of the database was around 25,000 data points, of which 20% was used for validation data. Each network was trained at least 3 times to make sure the amount of luck was minimal. The design of the network were quite simple. The most successful networks were linear networks, but networks with a single hidden layer about the size as the number of inputs were also tried. As the error metric, the mean absolute error was chosen. This was done because, for example, the root mean square error places a lot more emphasis on outliers, which is not something we want. A relative error also wasn't chosen because the energy can, of course, have an offset, and that won't change anything physically. And thus, the relative error didn't make any sense. Finally, a couple of optimizers were also tried, and except for stochastic gradient descent, they all seem to work fine. So Adam was chosen since it is a popular, versatile, and modern optimizer. It was also discovered that a lower learning rate nearly always resulted in a significantly lower error. A learning rate of up to 10 to the minus 15 was tried, 10 to the minus 5 was tried, and even then a lower learning rate still seemed to improve the results. But the lower bound wasn't discovered since otherwise it took way too long to train. Here you can see, for example, a training like that. One of the interesting questions, of course, then is what kind of input should be used for the network. At a minimum, the same amount of proximity matrices and their associated eigenvalues should be generated as there are dimensions in the problem. But perhaps more inputs and thus having an overdetermined system can result in a better trained network. The answer sadly is no. Using more inputs usually results in a more inaccurate network, both for linear and non-linear networks. This might be because the overdetermination results in such a network results in a network that's slightly confused as to what inputs are more important than others. For example, a network with which had inputs of proximity matrices of order -2 and -3, and an error of half in characteristic energy, but a network with orders of -2, -3, -4 had 1.6 characteristic energy units of error. The optimal order of proximity matrices was also investigated, and generally a higher order of proximity matrices resulted in a worse result. For example, inputs of order -3 and -4 had a loss of 1.4 characteristic energy units, which of course is worse than the -2 and -3 we had. In this image you can see the predictions and the potential energy of a test in which I dragged a particle through a cell, so from top to bottom in this case. It is from a linear network which has inputs of order -2 and -3. The energy itself has quite a large offset, as you can see, but when you then look at the gradient, it's actually quite nice. Of course, not perfect, you can see these two spots here, but it matches quite nice. Well, perhaps you can improve this by adding a hidden layer, but sadly, this didn't work. The error metric stayed approximately the same, but for a network with an extra hidden layer of 4 times the input size, where discontinuities were seen in this test, as you can see here, where nearly discontinuity-like things. Well, this couldn't have been caused by the activation layer itself, since for the activation layer a soft plus activation layer was used, which is continuously differentiable and were determined to be the optimal activation layer in the previous paper. So the best results remained a linear network, and while they were not perfect, they were surprisingly good. So now a bit about the future and continuation of this project. The scope of this project initially was more on machine learning, but figuring out the potential energy turned out to be more difficult than anticipated. So this project could hopefully be the basis for another BEP student, which can focus more on machine learning. In such a project, better networks could be designed, but also networks which work on multiple cell waves could be designed. An adaptive learning rate could also be implemented, such that it starts with a high learning rate, but it becomes lower as the decline in error stagnates. This way you can get an even higher accuracy and perhaps even find the lower bound of the learning rate. Also, with hindsight, the choice to use Python as a programming language was also suboptimal. This is because Python is not really a fast programming language. This doesn't really have to be solved currently because it's still plenty fast, but if it were to be re-implemented in another language, it would be even faster and even larger databases could be generated. An easier option than rewriting it might be to look into a Python to machine code compiler, because then the existing code can just be used. Also, the current relaxation process works quite poorly on large open spaces due to the way the potential energy function is defined. This could hopefully be improved. One method that could be used, for example, is using a different potential energy function when relaxing the system than when calculating the eventual potential energy. But to conclude, this project was largely a success. A potential energy function and the surrounding framework were designed that is able to produce nice databases for machine learning and does so in a way that's significantly faster and easier to use than DFT simulations. I hope that whoever is the next BEP student of Mr. Kuhlmann, that they will find my work useful. And finally, I would like to thank you for listening.
Okay, thank you, Tim. Let's thank the speaker.
Thank you.
So you always get a virtual applause, Tim.
Yeah, it's a bit underwhelming, but I like it.
Okay, so for everyone attending, so this talk is open now for questions.
Yes.
Okay. Yeah, if there's no question yet, let me start with one question.
Of course.
Where I was a bit confused, and that was if you can go back to slide 14.
Yes.
You showed an equation that was quite essential. So it's the equation.
Oh yes, the proximity equation. Yes.
The proximities. Yeah. So the Rijk, I understand. So this is the proximity parcels I and J.
Yes.
For the exponent that you label O. So
yes.
The exponent for the proximity, there's a minus O exponent in there, and the I understand that there's an Rij, but what is the K?
The K stands for, you have a number of surrounding cells around the cell itself, and the K stands for which surrounding cell you pick. So, for example, if I go back here, I can maybe show it here. oh wait, I'm skipping forward. Wait a second, I'm going to go backwards. For example, if you look at, I'm going to, yes, for example here you have such a lattice, and for example, if you take Rij is for example the distance between this particle and this particle, and the K is then stands for one of the surrounding lattice, one of the surrounding cells. So for example, if K is 1, and we say that this is cell K, or cell 1, then this distance is used. So between this particle and this particle. So that is what the K stands for.
Yeah. So it's interaction between particles I and J, but let's say I is a particle always in the central unit cell, and then J,
yes.
You also allow particles for image cells, for mirror cells, but then it's labeled with a K different.
Yes, it's just notation. Yes.
Yeah.
Also important to note that it could also be that I and J is identical, and then of course K equals 0, which is the central cell itself won't be taken into account, since otherwise you have it divided by 0.
Yeah. Clear. Yeah. Thank you.
Maybe I have a few general questions, if you don't mind.
Of course.
Because I'm not a machine learning expert, but I'm very interested in the potential energy surface, how you approach it.
Yes.
And you have given a very enthusiastic presentation. Thank you for that. So I want to ask you that from very beginning, so you use a toy model to do the machine learning and also to construct this potential surface, the energy surface.
Yes.
And do you have the toy model are based on a model out there in the literature, or you constructed yourself from zero?
It was partial. The toy model is not based on anything, but it is constructed partially from existing toy models. As I said before, the eventual potential energy that we used is a sort of modified Lennard-Jones potential that also works for triangles, for triplet interactions, and just the sum of taking each triangle, that is also a common approach used in toy models.
Yeah, so this triangle, is it meant to model a three-body interaction?
Yes.
Yeah, and what about the long-range interaction? Think about the except the pair interactions, three-body, but there are also long-range interaction. How do you take into account in that?
Yes, there are also higher. I believe you asked what about, for example, quadruplet interactions, right?
Yeah, more,
yes.
And even more than that.
Yes, these were not taken into account because triplet interaction is already quite complex. And besides, if we were to take that into account, then the amount of computations needed would scale to the power 4, which is even larger, and that would make this. This algorithm that I designed is also not 100% applicable to very large number of particles, but then it would be even less so. So it was this, chosen to.
Really a toy model. Yeah.
Yes, but it's still quite complex. So that we don't have 4-particle interaction is not a disaster.
Yeah, I can understand.
Yeah.
Yeah, and once you said you have actually spent a lot of time to understand the potential energy surface there. What is the most challenging part for you to? Yeah.
Well, there was a lot of trial and error with regards to finding out. I'll quickly go to the potential energy itself. There was a lot of challenges with regards to finding a good one. For example, with this, several potential energy functions were tried, and each time something went wrong, and it was a lot of trouble finding what exactly went wrong. So, for example, as you told, here we had bad convergence, and it was hard to find out why the convergence was bad. And with this, the problem was that the repulsion between two particles in itself wasn't good, and this resulted in particles that were very close to each other, and such a thing. There were also a lot of other potential energy functions which aren't shown here, which were also tried, but a lot of time was spent in finding out where it didn't work.
Yeah, itself is a very complex topic itself, I think, I believe, yeah.
Yeah.
Yeah, and in practice, when you do this project, you actually made a small program yourself, right?
Yes.
Is it also from scratch, or it's also adapted from existing code?
It is basic. Yeah, it uses some modules. It's written in Python. It uses. I can show you here. Wait a second. I believe. Yes. This is This is the structure of the code, as you can see. It is basically made from scratch. It uses some of existing modules, but those are mostly modules that help me with the math. So I haven't implemented an algorithm to calculate eigenvalues myself. I just used an existing module that also exists in Python. But the process itself was designed and coded myself, yes.
Could be a little more specific of which parts you implemented newly and which parts you actually... what existing?
Sorry,
I have some background noise. I'll just mute myself now.
Yes. Oh, sorry, I can't hear you now.
I have a lot of background noise now, but you can talk. I can hear you.
Oh, okay, yes.
Yeah.
As you can see the structure here, basically everything here was written from scratch. And of course, it all starts, you start by, first of all, running the program itself. That's on top of here. And this part basically starts the actual database generation. It does this here, and during a database generation, first the entire particle space is generated. That is all done from scratch. Then it's going to calculate for each of those data points, it's going to calculate the potential energy, so it's going to construct all those triangles and pairs and their associated energy. That is done here, and that is also completely written from scratch. And that also uses the lengths between the particles, and yeah, that is not complex. For that I just used a NumPy implemented function, which is able to, between two factors, find the distance, so that's not very complex.
Yeah. Is the code itself approximately how much lines? I'm just curious.
To be honest, I haven't checked that. I don't know, but it's it's not short. It's quite a few lines. I don't know how many, but I would bet it's more than 500. But I wouldn't bet anything on it.
Yeah. Okay, my last question. It's also quite a long question, perhaps. Because I'm a DFT expert, so I'm really, when we fit the potential energy, we really totally use a different approach. First, the general DFT data are specific system, and then we use that to fit the data and everything like that. And how do you say, the model now you use, how do you say that, not extend to a DFT approach, but how do you say that if I want to extend to a real material system, what is the next step? What is the challenge? How to bridge that?
Well,
we know you have a simple particles there.
Yes, indeed. Well, first of all, what you can do, of course, is the code that I had written is first of all very modular. So you can easily, for example, swap out the potential energy function. For example, if you don't like this modified, if you don't like the modified Lennard-Jones potential, then you can swap it out for another one, which is more general or more specific to a certain material. Also, the modified Lennard-Jones potential has a few parameters which you can tweak to sort of match the real potential of real particles. Yes, and of course you can also, while currently not in it, you can also, I think you can also quite easily implement a system where you can specify if a particle is a certain type of atom, for example. That's also quite easy to implement. And then, of course, you can adjust your potential energy function again such that it takes that into account.
Yeah, I think when you really define a type of atom, then you really need a initial input from DFT again, I think, in that case.
Yeah.
Because a type of atom interaction that you cannot just, how to say, put a random number there like that. Yeah.
Yes.
Yeah. Thank you. I answered all my questions for now.
For now, okay.
Yes.
Yeah. So anyone else who has a question for Tim? I don't think I see no one unmuting.
I also hear no one. So
yeah. Tim, can you explain explain a little bit the soft plus, why you selected the soft plus activation in the neural network?
Well, there are several reasons for it. First of all, because the paper of your previous student recommended it to me. That's the largest factor. But also, we needed, for example, in the course that you gave about machine learning, we used values, so that is discontinuous. The derivative of that is discontinuous, and we don't want that, because we want the network to also output a continuous or continuously differentiable, give continuously differentiable output, and with values that's not possible. So then a activation layer which does use, which is continuously differentiable should be used, and there are several options for that. For example, soft plus, leaky soft plus was also an option that was also used. And there's also a modified value which is also continuous, and some hyperbolic functions are also used. But in the end, the decision for soft plus was made because the previous paper recommended it to me.
Yeah. Okay.
Yeah.
Okay. If there are no further questions, then let's thank the speaker again.
Yeah.
So this for the time being, by the way, this is, I think, the last presentation for the summer. I think there's one or two more student presentations to come, but that will probably be in the month of August. But in any case, all of you will get an invite. Paul will send out an invite at least a week prior to the presentations happening. So, okay, thank you all for attending, and Tim, once more, thank you.
Yes.
And I will get back to you on the further procedure, Tim.
Yes, thank you.
Yeah.
Have a nice day.
Yeah, thank you. Suksha, I will make a separate call to you if you still have a few minutes time.
Yeah.